Can you guys hear me? Just a thumbs up or okay, cool. Okay, so welcome to MTC's Midsem workshop. This is for digital design. My name is Reuben, and I'll be teaching you guys today. So before we begin, I just wanted to ask you guys a couple of questions. So the first thing is, where are you guys at right now in terms of what you're being taught at class? Like, have you guys finished encoders? Or are you guys at
Yeah,
multiplex?
this PPT is finished.
You finished encoders
Yeah.
and you're at multiplexers now?
Yeah, in the lab we did multiplexes, but it's not discussed in the class.
So in class, okay, wait, let me see. So you've done encoders. That means, have you done adders, subtractors?
Yes.
Okay, but you haven't done multiplexers yet.
No, not in class. The teacher has explained in lab.
Okay, fine. All right, so for your midsem portions, most likely they'll ask only till encoders, prior to encoders, including adders, subtractors. I think for multiplexes and demultiplexes, they might ask for quiz too. So yeah, I think I'll teach you guys till encoders, and that'll be for your midterms. Um, okay, fine. So before we start, do you guys have any specific doubts you want to clear up before, or do you guys want to go from, let's say, the most important concepts of midsem? What do you guys want to do? If you guys just want to like start from, let's say, not the basics, but like just a quick run through the basics, and then we can go with important concepts for midsem. Would you guys be okay with
Yeah,
that?
that would be cool.
Okay, cool. All right. So from personal experience, what I've understood is one of the most important things you could do for uh, a BITS exam is to go through their PYQs. Yeah. So because personally, I feel like most of the questions that they ask from PYQs is almost repeated, not exactly the same, but almost the same every year. You also get a sort of an understanding on what sort of concepts they're trying to test you guys on mostly. So I've taken the liberty of pulling up two PYQs. So this is from my semester, and then on the right, you guys can see my screen, yeah, like a split screen. Like you can see two papers.
Yes.
Okay, cool. So on the left is my semester's paper, on the right is the sem before that. So I'll just quickly go through the layout of these two papers, so you guys can also see sort of how, not similar, but you can see the sort of similarities between them. First of all, we'll just go to the left paper. So you can see that they're asking us to design a combinational circuit. The second one is a word problem, but whenever you see a word problem, it's essentially telling you to design some sort of circuit based on the problem that they've given. So that is also designing some sort of combinational circuit. Third one is a full adder circuit, which also comes under combinational. Fourth is half adders. Fifth is encoders. Sixth is also encoders and decoders. Seventh is comparators. Eighth is Hamming code. So you can see that almost like 95% of these questions are about combinational circuits. Even if you look at the paper on your right, the first is a combinational circuit, comparator. Okay, and they also ask about your Hamming code and your parity generator, which is another concept they ask besides combinational circuits. Fourth is also about your Hamming code, and yeah. Fifth is about half adders. Sixth is combinational. Seventh is decoder. Eighth is Verilog. I don't think they'll ask you Verilog because they didn't ask for my semester as well. They might leave Verilog for the midsem exam for your lab. And ninth is also a word problem. So point being is they tend to ask questions that are only related to combinational circuits. So that's what we'll be focusing on mainly for this session. Uh, to do combinational circuits, there are a couple of basics that you guys need to know. You guys might already know this from your quiz one, but we'll just go over them quickly. Number one is your K maps, yeah. So you guys can see the whiteboard, like Hold on. Can you guys see me writing here?
Yes.
All right, cool. So I'll just quickly go over the basics of a K-map because, to be very frank, K-map is like your bread and butter in DD. Like you will, for almost every single question, you may have to draw a K-map because it's a very easy way of trying to visualize the circuits you're going to draw. So a K-map is essentially a way of describing some sort of Boolean expression, yeah, or even a truth table. So let's say you have a Boolean expression of um, sorry, it's a way to get a Boolean expression from a truth table. So let's say you have a truth table of A, B, and C, and you're trying to get some output. Let's just say X, Y. Why not? So A, B, and C, we can first off write it off by saying 0, 0, 0, 0, 1, 1, 1, 1. Then we do it 2 times. So 0, 0, 1, 1, 0, 0, 1, 1. Then we just invert it. This is the sort of truth table that you guys will end up having. And then let's say some arbitrary, let's say you're trying to implement a full ladder circuit, yeah? So instead of X, let's say you have sum, and instead of Y, you have carry. This is just to show an example. So let's say, so sum of 0 is 0, 1, 1, 1, 1 is 0 with a carry. 0, 0, 0. This is 1, carry. This is also 1 with a carry. This is 1. Oops. So 1 with a carry. And this is 1, 1. And yeah. Carry, carry. So now when you try to draw a truth table, oops, you start out by writing 1 letter at the bottom and 2 letters up top. And yeah, this is your A dash, this is your A, this is your BC dash, BC, B dash. So yeah. And so when you try to number these, number the K-map, it's 0, 1, 3, then 2, right? And then it's 4, 5, 7, then 6. So what this basically means is if you're just having, let's say, A, B, and C, your first square over here is 0 because if A dash, B dash, C dash, this basically means 0. Your next one, it's A dash, B, C dash. No, wait, sorry, that's all the way. My bad, guys. It's B dash, C dash, yeah. So here what that basically means is A dash, B dash, C, which is basically just 1. That's why it's 1 over here. Similarly for A dash, B, and C, that is just essentially 3 if your B and C is 2 and 1. So that's essentially how we're getting these numbers. So now we have to draw 2 K-maps over here because we have 2 outputs. We have S and we have C. So if you're trying to plot out S, we just have to see which of these numbers have the value 1. So we can just, on the side, if you want, you can just write down what each number is in decimal. 5, 6, 7. So here we can see that 1, 2, 4, 5, 6, and 7 have 1. So it's 1, 2, 4, 5, 6, and 7 have numbers 1. So there are a couple of rules in when you're trying to group a K-map, numbers in a K-map. Number 1 rule is you try and go for the biggest group first. And you can only group in terms of it can be 1, 2, 4, or 8, which is just basically 2 raised to 0, 2 raised to 1, 2 raised to 2, and 2 raised to 3. You can also go up to 2 raised to 4, 16, but this is not that often. Or if you get this sort of 2 raised to 4, if you ever need to group 16 numbers, it'll be probably with a larger K map. So you try and see if you can find any sort of groups of 1, 2, 4, 8. So off the bat, I can see that there's one group here. I'll just take a different color. I'll take red. You can see there's one group here. Uh, Another group is here. There's just two. Another one is here. So 1 minute. Someone join. So we can see that there's essentially three groups over here. The bottommost group, which is just that four ones in a row, is essentially is this A bar, right? Because you have to look at the common term amongst all these ones, which is A bar. Similarly, for this group over here, see what are the common terms. Start off with the vertical column. Is there any common term here? There isn't, yeah, because one is A dash and the other one is, sorry, my bad, this is A. So there's no common term amongst the vertical columns. So you look at the horizontal column and you see what's the common term. It's B dash C. So you do B dash C. And then you look at the second group over here. Similarly, there's no common terms among the vertical column, but the common term amongst the horizontal column is uh, B C dash, right? So this is essentially your first Boolean expression from this truth table. This is for S. You do something similar for C. This is just one example. I'll just go through some types of, what do I say? Some different types of K-maps which you guys can encounter in exam. This. 1 minute. Oh, I gotta do page, bro. Okay, I'll just rub this off. Let's see what happens later. Okay, so we'll just go through some different types of K-maps, K-map groupings, which you guys can encounter in exam, which will just give you a better clarity on what to group and what you can't group. Yeah, we'll take the same example of our three inputs, which is A, B. We have A dash, we have A, and then you have our B, C dash. Here it will be B dash C, B, C, and it'll be your B, C dash. Yeah. So now let's say you have a one here, you have a one here, and you have a one here, and you have a one here. Let's say you have another one over here. So how would you guys group this? So one of the things about a K-map is you can also group uh, adjacent, but also the very end. So what I mean by that is you can essentially group this along with this, because you have to sort of imagine your K-map curving around. Instead of it looking as a flat plane, you can sort of imagine as sort of a circular sort of cylinder as such, right? Imagine this is just a K-map. It's kind of just curving in on itself. So you have the liberty of also treating these two ends as your adjacent terms. So you have the choice to group these four terms as well as one group. You have this one remaining, so you can also take this as a group. So you have essentially two groups over here. This is one sort of case. However, suppose you have, let's let's say you have a 1 here and you have a 1 here, you cannot take a group like this. Because what you're essentially doing is you have, let's say, 1 here and 1 here. What you're essentially doing is you're taking a group like this. This, you can't diagonally group any pair. That's not possible. It has to be either exactly vertical or exactly horizontal. You can't do diagonally at all. So that's one rule to K-map. And is there anything else? Suppose let's say you have 1, 1, 1, 1, and 1, 1 here. You can also take this. No, I'm sorry, you can't. You can take this as a group. You can take this also as a group, which is 4. People may ask, if you've grouped this as 4, why can't we just group this as a 2? You guys have to keep in mind that we're always trying to get the maximum number of terms in a single group. So even though we could pair it as 4 and 2 like this, when we have the opportunity to pair it as a group of 4, we go ahead with that. And another thing is, suppose you have, let's say, a 1, 1 over here. Then we can stop this off. So normally what people would do is you would group this as 4 and you would group this as a 4 as well. What you cannot do is when you're grouping, so over here you can see that this ones are getting overlapped essentially, so they're getting grouped twice. This is fine as long as you keep in mind that you never group the entire group more than once. What I mean by that is, let's just give an example. Let's see a quick example. Suppose you have something like this. How do I draw this? You have, let's hold one here. Okay, I'm just giving a hypothetical situation. Suppose you group a group like this, and you group the remaining ones in vertical columns like this. So first of all, this is wrong for numerous reasons, but one of the reasons this is wrong is because you've grouped this horizontal column, which I'll just highlight in red, or yellow. I'll just highlight in yellow. You've grouped this horizontal column of ones 2 times. The entire group, you've grouped it along. You've grouped it 2 times in the sense you grouped it 1 time in this horizontal column or horizontal row, and you've grouped it with this vertical row. So basically, the rule is you cannot group an entire group of ones more than 1 time. So just to give another hypothetical example is, for example, let's just say you did something like this. Now talking about that specific rule of not grouping the entire group more than once, this is correct because you've left this one sort of free, right? This is like a very extremely rare case, so you guys don't have to worry too much about that. Another thing about K-maps is you have a thing called don't cares. You guys should have come across them by now in your quiz. Don't care is essentially like it acts as a 1, but the only thing is you don't necessarily have to group it with the rest of the ones. Yeah. So again, I'll just give an example. Oops. How many guys? So okay. So suppose you have a K-map. This time I'll take a 4 variable K-map. A, B, C, D. You have A dash, B dash. You have A dash, B. You have A, B. A, B dash. And then you have here C dash C. CD dash. This is a 4 input K map. So when you're numbering this, there's also a small thing to remember. So it's 0, 1, 3, 2, 4, 5, 7, 6, like before. Now remember that when you're numbering it, you should go to the lastmost row, not to the third row. So it'll be 8, 9, 11, 10, 12, 13, 15, 14, right? This is a thing to keep in mind of. So now about don't cares, right? So let's just say you have some sort of numbering, like let's say you have a don't care here, a one here, don't care here, don't care here, one, one, so one here as well. So now let's try and find a way on how to group this here. Let's start with the biggest group first. So off the bat, I can see that there is a group of 4 that I can create by essentially going like this against each of the corners. Yeah. So essentially over here, I had taken 2 ones and 2 don't cares. And now going for the next biggest row, I can take these because it creates a group of 4. So here I'm using 3 ones and 1 don't care. And the next I can take is just individual ones. Now, this is the most optimum way of getting a Boolean expression. If I were to write it down quickly, the biggest row, look at the common terms. So the common terms along the horizontal row is you have A dash, B dash, and then looking at the horizontal rows, you can see that B dash is a common term, right? It's there in both the rows where essentially like a diagonal square is. So we can say B dash. And looking at the vertical rows, look at the common term, we can see that it is D dash, right? So it's B dash, D dash. So this is essentially representing our group of 4. Now, if we just move this, okay, now looking at our next largest group, which is also a group of 4, but the horizontal row. Over there, we can see we're trying to find the common term. There's no common term amongst the vertical columns, but if you look at the horizontal column, we have A B dash. So we can just write that down as A B dash. And then looking at our individual groups or individual terms, it's just what is written at both the horizontal and vertical column, horizontal row and vertical columns. So that is A dash B, C dash, D dash. Similarly for the other term, it is A dash B, C D. Right. Now, one thing to note here is I didn't take this don't care as a separate term itself, because in the name we don't care about it. So we only care about it when we can group it along with other one terms to make a bigger group essentially. That's the only purpose of don't care. Otherwise, if we had to choose a don't care by itself, we don't do that, and that's not how we do a K-map. This is our Boolean expression from this K-map. So I think I've covered all the basics of a K-map and all the different scenarios you could sort of reach with a K-map. So with that, I'll just quickly go ahead with all the different types of combination circuits that you guys could face in an exam. So I have a Google Drive here. I'll be sharing this with you guys at the end. This Google Drive has answer keys from previous year papers, has class notes from a friend, has lab notes, PPTs. I think we have 2 PPTs. We have Ashutos's PPTs and another professor's PPTs. I'm not sure which one it is. The tutorial, we have the answers as well. So it's a great document for you guys to go through. I'll be sharing this with you guys in the chat as well. And I'll also be sharing it with an email that MTC will be sending you guys. So yeah. So now just going to the PPTs, I'll just quickly go through, I think it starts from here. Yeah, okay. We'll just quickly go through the combinational circuit types, yeah. So this is just an example. We're starting off with the comparator. So a comparator essentially compares two inputs. Yeah. Now these two inputs could be 1 bit, 2 bit, 3 bit, 4 bit, 5 bit. It can be any number of bits. But let's start off with a 1 bit comparator. So a comparator can have three outputs. It can give one output when A is greater than B. It can give one output when A is equal to B. And it can give another output when A is less than B. Now you can create a truth table like this, right? And you can form the K maps. And when you find the Boolean expressions, you can create a digital circuit like this. By the way, I'll do I'll make a comparator K map truth table and circuit right now for 2-bit comparator, just to give you guys an idea on how we can approach doing this. So let's say, let's keep this here, this. So for 2-bit comparator, you essentially have A1, A naught, and you have B1, B naught, right? Now, before you even get the outputs, you have to form your table. So this has four inputs, so that'll have 2 raised to the 4, which is 16 outputs, or like potential outputs, or potential combinations of your inputs, basically. So you essentially have 16 rows here. So it's pretty easy to just draw the different rows. You just follow the pattern. So the last most will just be uh, 8 zeros in a row. So it'll be 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8. It'll be 1, 2, 3, 4, 5. Oh, that's anyways. You can just see there'll be 8 ones in a row. Actually, I'll just make it neater. It's gonna annoy me. 0, 0, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. 1, 3, 4, 5, 6, 7, 8. Similarly, for the next one, you just do 4 zeros in a row and then 4 ones in a row and just repeat it until you reach the end. So it'll be 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. For the next one, it's just 2 zeros in a row and then 2 ones and 2 zeros. You repeat the same thing again until you reach the end. So 0, 1, 1, 0, 0, 1, 1. And then here just keep alternating between 0 and 1 to get your this column filled. So it's pretty straightforward on how you can on how you fill this up. Essentially, okay. Now, in terms of output, like I said, you can have three outputs. You can have when it's greater than, you can have when it's equal to, or you can have when it's lesser than. So the way you sort of compare this is by just looking at the two numbers. So essentially, these are two numbers, essentially two-digit number, yeah, but in binary terms. You look at the first term, you see that they're equal, so you give this a 1. Here you see that this is for when A is, you're comparing in terms of A. So here A is lesser than B. So essentially A is lesser than B, so this is 1. And you essentially just create this truth table. I'm not going to do the entirety of it because it's going to take a little too long. But yeah, essentially I think it's here as well. Yeah, it's going to be this. This is quite big, but yeah, this is what your truth table will end up looking like, and this is what your K maps will also end up looking like. And you'll have to draw this. So once you get your Boolean expressions from your K maps, you can just draw a digital design circuit like this. Now, they will ask in exams to draw a 3-bit comparator or a 4-bit comparator. And you can see just by doing a 2-bit comparator itself, it's quite intensive, time intensive. So how do we sort of make this quicker? So the way you do this is by analyzing a pattern from these comparators. I'll show that pattern to you guys. So you can make this a little quicker by noticing that in a comparative circuit, for your equal for equal whenever your terms are equal, it follows the pattern of uh, let's say you have a 2-bit. Let's say you have A1 A0 and you have B1 B0. It's equal when A1 X nor and B1 and A naught X naught B naught. So this essentially gives you your output for when it is equal to, right? So when your A is equal to B. Now let's say instead of 2 bits, you had 3 bits. So you had A2 and you had B2 as well. So the easy way of doing this is by just changing a Boolean expression to A2 X naught B2. This is a very easy way of, instead of doing the whole truth table K-map and then getting a Boolean expression, this is an easy way to sort of remember. This is a pattern that it follows. And similarly, even for lesser than, or let's start off with greater than, it follows a pattern. The pattern is this. We go from the most significant bit to the least significant bit, right? You just go from left to right. You compare the two bits individually. You check if A2 is greater than B2. If A2 is greater than B2, we say that it is A2 B2 dash, because A2 is 1, B2 dash is 0. So that's one sort of situation where it's greater than. If let's say instead A2 is A2 and B2 are equal, then let's give this term. It's essentially mimicking this term, right? Let's give this term the value of x1. So we can say A2 and B2 are equal. So we say it's x1, which is essentially just A2 nor B2. And then we look at the second bit. We can see now instead, let's say A1 is greater than B1. So it's A1 greater than B1. So when it's this, then again, the greater than condition is satisfied. However, if let's say your A1 and your B1 bits are equal, which is this condition, let's call it x2, then we can have a third sort of scenario. So let's say your A2 and B2 bits are equal. Your A1 and B1 bits are also equal. So that's x1, x2. And you could your your A0 and your B0 bits. Now let's say your A0 bit is greater than your B0 bit, which is B naught dash. This is also going to give you greater than. So we've essentially created a Boolean expression for your greater than logic for a 3-bit comparator. And this is by using your 1-bit comparator logic, which is adding on to it. Similarly, for your lesser than, it's the same thing. Only thing you flip the dash. So instead of looking at if A2 is greater than B2, we check if A2 is lesser than B2, right? So here B2 is 1, A2 is 0. So that means B2 is greater. So that satisfies when your A is lesser than B. Similarly, you just do the same thing for the rest of the scenarios. So just basically shift the signs up. It's not it's A dash 1 B1 plus x1 x2 A naught dash B naught. This is for your lesser than. So this is one way in which you can quickly find the Boolean expressions for multiple bit comparators. So now let's say instead of having 3 bits, you have 4 bits. So the way you would do this is, again, just treat it as if you're doing it 1 bit individually and then just add on to the logic. So let's say you had 4 bits. Let's say you had 4 bits. Let's say you had A3, A2, A1, A0, B3, B2, B1, and B0. First things, when you're looking for equal to, just take X NOR of everything. So the A3, X NOR B3, and it's and in between each scenario. Oops. Uh, Similarly for you do B2 X NOR my god, A2 X NOR B2, and then and A1 X NOR B1 and A0 X NOR B0. This is for equal to. Similarly, like before, for the 3-bit, for the 4-bit as well, you take this as your X4, you take this as your X3, you take this as your X2, you take this as your X1. So again, for a greater than, you can just assume taking it from the most significant to the least significant. You can just compare and add up the terms. And so that's one way of doing a comparative circuit. I think if you look at the slides, it's something similar over here as well. So yeah, you can just get a Boolean expression. You can draw it here, circuits like this. And that's basically your comparator. Now we move on to decoders. So for a decoder, it basically means you have multiple input lines and you have essentially uh, some amount of input lines, and you get basically encoded input lines, and you decode the input lines into some sort of tangible output. So the way we normally work is you have some n input lines and you get 2 raised to n output lines. So let's say you have 2 input lines, you will get 2 raised to n, which is 2 raised to 2, which is 4 output lines. That's essentially how a decoder works. So this is the truth table for your decoder. So when it's 0, when A and B are 0 and 0, your D1, so you get essentially an output of D0. If you input A as 0 and B as 1, you get an input of D1. If you input A as 1 and B as 0, you get an input of D2, output of D2. And if you input A as 1 and B as 1, you get an output of D3. You can do this for, let's say, an input of 3. So you have A, B, C as your inputs. You have an output of 8 instead of 4 this time, right? And that is essentially your decoder. You can also, along with your inputs, have an enable pin. An enable pin is essentially just like a switch. Yeah, you just switch it on and off. So if you enable is 0, then it's switched off. If it's 1, it's switched on. And yeah, this is a very important question which they will ask for exams. It's essentially trying to create a larger decoder or a larger encoder by using a smaller type of decoder encoder, right? It's a question that they like asking a lot, and it's pretty straightforward. It's pretty simple. I think it's better if we solve this with a previous paper question. Previous paper question, just to show you what sort of how they could ask you this type of question, right? So I'll see from here. I'll take from here actually. Let's see. So yeah, see. So they're asking you to construct a 5 to 32 line decoder using 3 to 8 line decoders with enable and a 2 to 4 line decoder. And they're asking you to draw only block diagrams. They don't want you to draw the entire circuit because a decoder is essentially just a circuit diagram, yeah. But instead of just drawing your entire circuit diagram, you can just draw a box as such, and you can just give 2 input lines and you can have 4 output lines, and you can just say this is a 2x4 decoder. This is a much more easier way of representing instead of drawing the entire circuit diagram. So let's try tackling this question. Let's see if we can get it right. So they want essentially a 32 output. They want essentially 32 outputs from 5 inputs, and they're asking us to use 3:8. So off the bat, I can see that if we have two of these 3:8 decoders, we can get 132 output. Yeah, what I mean by that is, let me just fill this out. So let's say I've had, not sorry, not two, let's say I have four. So we have 8 outputs, 1, 2, 3. Actually, I'll just draw this closer to the end. Say I had one decoder here. We have 1, 2, 3, 4, 5, 6, 7, 8. We have another one here. One, and I'll just draw this. So zero. This is zero. This is seven. This is sorry. This is zero. This is seven. This be 8. Let this be what is it? 8, 6, 15. We have 16. Right. Just add 7. 23. Then we have one more here. Just 24. Have. Not bad. 32. So essentially, you'll have your 3:8 decoders over here. This is actually 31, my bad. 3:8 and 3:8. Right? So if we have four of these, we essentially have a 32 output decoder. Yeah. We have now 3 inputs for each of these four. So the way I'm going to figure this out is, how do I connect these inputs? I have, let's see, 3 into 5, 12 inputs. How do I connect this to get our 32 output? They're also telling me in the question to use 2:4 line decoder. So 2:4 line decoder, and there's also an enable pin here, by the way. There's an enable pin along with your 3 inputs. So off the bat, I can see that if I have a 2x4 decoder, I have 4 outputs and I have 4 decoders. So now let's just say I connect each of these outputs to my enable pins, to each of my 3x8 decoders, right? And I have 2 inputs here. So now let's see, I have essentially 2 inputs over here, and I have 3 inputs each for my 3x8 decoders. So what this basically means is, if let's say these inputs for my 2x4 are A and B, if let's say for example my A and B are 0 and 0, that means this line gets activated. If this line gets activated, this decoder gets activated, and all of my other decoders are deactivated, right? Because my enable pin is 0. So if this decoder, my first decoder, is activated, that means now depending on the input from these 3 inputs of my 3x8, let's call them C, D, and E. Depending on these inputs, I can get from 0 to 7, right? So if I were to draw a truth table about this, it'll be A, B, C, D, E. So my A and B are 0. Let's say my C is 0, D is 0, and E is 1. That essentially means my first output is activated. So my 0 is activated. Instead of E being 1, let's say instead my C is, sorry, 1 minute guys. Yeah, my C is activated. So my C is activated. That means my fourth one, 0, 1, 2, 3. So my fourth output is activated. Now, instead of let's say instead of having my A and B as 0, let's change it up. Yeah, let's make my A and B 1 and 1. So my A and B is 1 and 1. That means that only my fourth line is activated. If my fourth line is activated, that means my enable pin is, my fourth decoder is activated over here. Now let's see, my A is activated, my B is activated, my C is also activated. If my C is activated, that means the fourth output of my 3x8 decoder is activated. So 24, 25, 26, 27. So my output will be 27. So you can see that we've essentially created a 5x3 what do you say, 5x3 decoder from using 3x8 decoders and a 2x4 decoder. Essentially what we've done is we've taken A and B as our two most significant bits as the inputs for the 2x4 decoder, and the three least significant bits we've taken as the input for our other 3x8 decoder. So this will be a C, D, and E. I think an easier way to just point this out would be by just taking three lines C, D, and E and just connecting them, so drawing lines like this. Just draw lines and just connect your C, D, and E, C, D, and your E. Sorry for not being so neat, guys, but this is essentially an easier way of connecting your input lines. So this is one question where they're trying to make you create a bigger sort of decoder by using a smaller decoder. So it's a very, very short question. In fact, I think even this paper from last year in my semester, I think they've given a similar question. Yeah, so here they're given a 3x8 from 2x4. This is relatively simpler. The same thing. You just have to essentially use your smaller decoder as your enable for your other. Here it's the same size, but in the example which I just solved, you use your smaller decoder as your enable control, right? Enabling which decoder to get activated and allowing your larger decoder to be your outputs. So yeah, this is one short question that they will ask you guys. So moving on from decoders, yeah, that's it, I think. So those questions. So now we'll move on to your encoders. Encoders are basically the opposite of your decoders. So encoder, basically you have n number of bit lines, and you have so you have 2 raised to n number of input lines, and you have n number of outputs. So let's say you have 8 input lines, you have 2 raised to 3, which is 8. So you have 3 output lines, right? Just so you can see here, they've given an example of 4:2 encoder. So you have 4 input, you have 2 outputs. So if your inputs are D3, D2, D1, and D0, depending on which of your inputs are activated, your output will be such. Now there's a small issue here, and that is as written over here. If, for example, let's say your D3 and your D1 is both 1, right? Then which output gets activated? Is it this one? Is it, sorry, I'll draw down actually. So let's say you have a situation where you have D3, D2, D1, D0, and you have your outputs as Q1, Q0, as is written over here. You have 0, 0, 0, 1, you have 0, 0, 1, 0, you have 0, 1, 0, 0, and you have 0, 0, 0, and 0. So here it'll be 0, 0, 0, 1, 1, 0, and also here it'll be 1, 1. It'll be 1, 1, yeah. So now instead of, this is like a perfect scenario, but instead of having this, let's say instead you have D3 and D2 as activated over here. So now how do we decide if this gets activated or if this gets activated? Because both of our D2 and D3 are high. Do we get this output, or do we get that output? Or do we get this output, or do we get this output? So this is where we use priority encoders. Priority encoders basically means we give a sort of hierarchy to the inputs. We give a certain significance to one input than the other input. So if you're talking about this particular problem, let's say that I've given D2 my highest priority. Then I've given D1. Then let's say I've given D3, what is happening to my handwriting today? D3, and you have D0. So if you have this sort of hierarchy, then you look at your truth table again. We can say that D2 and D3 are both active. So we look at our hierarchy, we can see that D2 has a higher priority than D3. So what that means is my D2 will fire. So my D2's output is essentially this one. So this output will fire when Q1 is 1 and Q0 is 0. This is how a priority encoder using a hierarchy of their inputs solves this issue. So again, with priority encoders, they have a tendency to ask this question, and they have a tendency to ask it in a number of ways. We'll just solve a couple of PBC paper questions depending on this. This should give you guys an idea. So yeah, this is a priority encoder. So let's see. Any encoder questions here? Priority. There's no priority encoder here. Let's check here. Yeah, so here's a question. So they're asking you to design a 4 to 2 priority encoder, and the order of priority is D2, D3, D0, D1. So as you can see, and they're also telling you that your truth table should be such a way that D3 is MSB and your D0 is LSB. Now, this is one way they could ask it, or they can also have the liberty to ask you to ensure that, let's say, you have to write the truth table in D2, then D0, D1, and D3. They can also ask you to write it like that. They what they want to do is try to understand your depth of knowledge in that question. So there are different sort of permutations and combinations of the way they can ask this question. This is just one way. So here they've given D2 as your priority, D3, and then D0, and then D1. So what this basically means is if we were to draw our truth table, I'm gonna guess, have a easier solution. Right, so if you were to make it a little easier, you don't have to draw this entire truth table for your solution. What you could do instead is you can write here. So here they want your D3 to be a most significant bit, and then you want your D0 to be a least significant bit. So it can be D3, D2, D1, D0. And your outputs are X, Y, and V. V is basically a valid bit. By this, what we mean is, let's say your, what do you say? Your inputs is all 0. If it's all 0, it doesn't have any meaning to it. So your validity is 0. It just basically sort of ensures that if you're not giving any input to your encoder, it doesn't matter about the output. Yeah, that's just what this validity is. Basically, what that means is the validity is always 0 if your input to your encoder is 0, and we essentially don't care about the output. Otherwise, for all other cases, your validity is 1. So now let's see. So they're asking here that D2 is your priority. So what that means is, let's keep D2 as 1. And now what it says, we don't care about any of the other conditions. We don't care about D3, we don't care about D1, we don't care about D0. If your D2 is 1, that means your output will be 0, 0, and your validity is 1, right? Now let's say your next priority is D3. So let's say your D3 is 1, and your D2 should be 0, right? Remember, if your D2 is 1, then we go to this condition where we don't care about the values of D3, D1, or D0. So if your D3 is 1 and your D2 is 0, and we don't care about D1 or D0, then our output is 0 and 1, validity is 1. Going to the next one, which is D0. So now remember, D3 should be 0, D2 should be 0, D1 we don't care about. If your D0 is 1, then your output is 1, 0, and the validity is also 0. This is also 1, right? Now going to a final thing where D1 is your least least on the priority. So here everything should be 0, right? Except for D1, which is 1. Only then we'll get an output of 1, 1, and the validity is 1. Right. So this is a simplified truth table that you guys can draw. It's essentially the same thing as this, which is given the answer key. This is more shorter form. What I've done basically is I've essentially a don't care basically means this can be either a 0 or this can be a 1. So if we, for each of these scenarios, if we take it as 0 and 1, you will have this expanded truth table. But it'll be a little tricky while drawing the K-map. You need a little practice if you're using this truth table. If you guys aren't confident, you guys can then go with this longer truth table as well. It's dependent on you guys. And yeah, so then you guys can just draw the truth table. Remember, there will be 3 outputs. You have to draw one truth table for your X, one for your Y, one for your V as well. This is something people got wrong a lot for like my semester, including me. People forgot to draw a K-map for the V as well. And yeah, so once you draw that, you can get your expression. You can draw a circuit as well. I think here they didn't ask. They did ask. I don't know why they didn't draw circuit, but if you draw circuit, but yeah, once you get the expressions, you can draw a circuit as well. And yeah, don't forget your don't cares as well, because you have a don't care for your very first condition, where your D3, D2, D1, and D0 are all 0. So don't care here. And it's important because you use it to create your Boolean expression over here. Right, so that is another pretty important question that they can ask, priority encoders. Multiplex and demultiplexes, I'm pretty sure they won't ask you guys, because they haven't asked in the previous two years of DD Midsem. So yeah, moving on to the next one. We've done comparator decoder. This is yeah, this is full adder and half adder. This is your final form, final type of combination circuit design they can ask you. So a couple of things to remember over here is to learn these circuits for half adder. So we know a half adder essentially is this in a block diagram sense. Remember what a sum means and what a carry means. So if I were to draw over here, so this is your this is a full adder. If I wanted a half adder, is it here? It's not here. Okay, anyway, so let's say a half adder is this. And you have 2 inputs, A and B. You have an output, let's say sum for now. And you have an output of Cn. This is your half adder, by the way. Yeah? This is easy to write, but just remember what a sum actually means. So here a sum essentially means A XOR B, and your Cn means A product B. The reason why this is important to remember is they have asked people to essentially use half adders, full adders, half subtractors, full subtractors in creating Boolean expressions. I'll show an example of that question soon. And you essentially need to know what your outputs indicate. You need to know that a sum indicates an XOR B, and your Cn indicates A dot B. Similarly, for a full adder, right? A full adder has 3 inputs. You have A, you have B, and you have a Cn. You have an output of sum, and you have output of C out. Similarly, over here, the sum essentially means, if I remember, it's here somewhere. Yeah, your sum essentially means the XOR of all your inputs. And your C out means A dot B, which is this, or your Cn A XOR B. Now, these Boolean expressions are not just randomly appear. They have what do you call, you create a truth table and you can create a Boolean expressions. But instead of doing it in exam itself, it's better to just remember this. It's not that hard to remember because you're getting it from the half adder itself. You're just adding onto it, and it's relatively easy to remember, and it'll help you guys a lot if you remember what exactly your outputs mean, Boolean expression wise. So similarly, even for the subtractor. Yeah, so your subtractor difference is also a x XOR y, but your b is, I'll just write it down here. So let's just say suppose you have a half subtractor, you have a full subtractor. So again, your half subtractor has two outputs. You have a difference and you have a borrow. Similarly here also, this will be a borrow in, this will be a borrow out. This will also be difference, this will be borrow in. So again, a difference basically means A XOR B, and your borrow in basically means A instead of A and B, it'll be A and B dash. That's the only difference you guys have to remember. Similarly, for a full subtractor, it's here somewhere. Where is it? It's not given. Yeah, it's here. It's just the same thing. So it's A XOR B XOR B in. The same thing as your full adder. And your B out is the same thing as before. It's just your. Actually, no, it's a little different. No, yeah, it's exactly the same. So it's your B in dash A XOR B, or just your this value. So A and B. So these are the two outputs for your full subtractor. So just remember these Boolean expressions. If you can't remember full subtractor, just remember the half subtractor and just add on to it, right? The same thing for your adder, half adder and full adder. Just remember these expressions and that'll be good. Just also remember how to draw a 4-bit ripple adder or parallel adder. They won't ask you the circuitry behind it, but they will ask you to use, or they will ask you to either draw this or they'll give some sort of condition. I'll show you an example of the question in the PVIQs. I think similarly also for adder cum subtractor. Essentially, this is a circuit diagram where you can perform both addition or subtraction depending on the value for m bit if given over here. If you put 0, it'll perform addition. If you put 1, it'll perform subtraction. And so this will give you, C will basically be your output. No, sorry, a C will be your carrier or your borrow. Your S0, S1, S2, S3 will be your outputs. Your A0, A0, A1, A2, A3, and your B0, B1, B2, B3 will be your inputs for your for your two numbers. This is for 4-bit. You can also have for 5 bits, 6 bits. It's up to you guys. Depends on the question actually. And yeah, this is BCD adder. I think it's better you guys learn this circuit as well. These are the sort of things you have to sort of learn. You can understand it. They've given truth tables over here, but in the exam, if they ask you to draw it, I think it's easier if you just draw it from memory rather than trying to understand and draw it, because it'll take too much time. And you guys have only 1.5 hours, so it'll take quite some time to just do it through logic. It's easier to learn at home by understanding the logic and then trying to draw it from memory in the exam hall itself. So this is your combinational circuit. I'll show some examples of where they can ask your half adders. So let's see here. So this is 3-bit. Here. So here they're saying to draw a 4-bit decrementer using full adder circuit. It decrements essentially 1 from 4 bits. So this is, again, what they've done is they've taken a full adder circuit, the exact same. I'll show you the picture of it. They've taken essentially a 4-bit parallel adder circuit and they've modified it a bit. So what they've done is they've taken one input as variable, which is A0, A1, A2, A3, and they've taken the other input as 1, right? And here they've given an input of 1 instead of 0 because they want to decrement the number which you input, which is A0, A1, A2, A3 by 1. So this is just one example. It's kind of tricky. Even I haven't exactly understood how they've done this, but this is a way that they can ask you to use the sort of circuit diagram that they've given to create some sort of different circuit. Similarly, over here, they're asking you to implement these Boolean expressions using the half adder. So this is where you knowing the outputs of your half adder come into play. Here they're saying to get A XOR B XOR C XOR. So as we know, a full adder, the sum of a full adder gives us exactly this, which is why they've taken two half adders, they've connected the both of them, and they've taken the output D, which is essentially the sum, as your answer for this one. Here they're asking you to take A dash BC plus AB dash C. Here, what you have to do is you have to manipulate it a little bit by using your Boolean algebra. Here they've taken, I believe, C out as common, and they've taken A dash B and AB dash in brackets, which is essentially just A XOR B, right? So XOR B into C. And from what we've learned, if you look over here, where is it? Is essentially just your full adder's output, right? So this is essentially how knowing the outputs of your half adders come in. That's why it's very important, actually. So yeah, that is your how you use your half adder and your full adder. And this is the decoder. We've covered this. This is a comparative question. So over here you can see they've taken two 3-bit inputs, right? And they're asking you to find equality, and they're asking you to find greater than. So they essentially split the question. Instead of asking you to find lesser than, they're asking you to find equality and greater than. So the trick, like I told before, just take it as one bit individually and then just keep adding it to your number of bits. So we've done a similar question like this before as well. And yeah. Okay, and the final concept which you guys need to know for Midsem is your Hamming code and your sort of identifying the error. So we'll just take this question as an example. And yeah. So here they've given us a Hamming code, and it is essentially 0, it is 0 0 1 0 0 1 0 1 0 0 1. So first things first, we have to identify how many parity bits are there in this Hamming code. Yeah. So we have an equation which is 2 raised to p greater than or equal to your parity bits plus your message bits plus 1. So we can see that your p plus m is 11 plus 1, which is 12. So 2 raised to p is greater than or equal to 12. Now we can just do by trial and error. Let's say p is 3. So it's 2 raised to 8, which is not greater than 12. What about 2 raised to 4, which is 16, which is greater than 12? So we can assume our parity bits to be 4. So we know that our parity bits are at the locations, are the locations 2 raised to 0, 2 raised to 1, 2 raised to 2, and 2 raised to 3. So essentially it's at position 1, position 2, position 4, and position 8. So it's this position, 2, 4, 5, 6, 7, 8. It's in these positions, right? And the other positions essentially are data bits. So we can just name this as P1, P2, P3, P4. This is a message 1, message 2, message 3, message 4 is here, message 5, message 6, message 7. So 7 plus 4 is 11. Yeah. So what we have to do first is for parity 1, we take the every alternate bit. So the way we can do this is by taking 1 minute, guys. Okay, guys, I'm back. All right. Yeah. So way we start off with is we look at the different parity bits. So for P1, we look at the bits 1, 3, 5, 7, and 9, and yeah, and 11. And we see what are our inputs. So we have, oops, sorry. So we know that this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11, right? So we look at our value at 1, which is 0. I'll just draw a column for each of these. So we can see it is 0, it is 1, it is 0, it is 0, it is 0, and it is 1. And is it odd or even? Is it even parity bit? So this is fine. So our error over here is 0. So we now look at P2. So P2, we look at every 2 bits. So we look at 0, 1. So here it's 0, comma, 2, 3 we leave out. We look at 4, 5. 0, 1 minute. We look at 0, 1. So I'm looking at my table. So 0, 1, 2, 3 we leave out. 4, 5, 6, 7, 8, 9. Right? Here, let's see. So here it's 0, 4, 5 is 0, 0, 8, 9 is 1, 0. So over here, this is having odd parity, so this is having an error. So we keep this as 1. We look at P3. Well, so P3, we take every 4 bits. So 0, 1, 2, 3, we leave. Oh, wait, 1 minute, guys. I made a mistake over here. It's not this. It's 0, 1, will be 2, 3, 4, 5 gets left. 6, 7, 8, 9, 10, 11. So this, we check. So 2 and 3 is 0, 1. 6 and 7 is 1 and 0. 10 and 11 is 0 and 1. So here we have an error of, because it's odd parity, its error is 1. Looking at 3, you can see 0, 1, 2, 3. So we check 4, 5, 6, 7, 8, 9, 10, 11 we leave out. So we check 4, 5, 6, 7. So 0, 0, 1, 0. So 0, 1, 0 also has an error, right? Finally, we check out P4. So in P4, we can see we leave out 0, 1, 2, 3, 4, 5, 6, 7. And we only check out 8, 9, 10, and 11. So 8 is 1, 9 is 0, 10 is 0, 11 is 1. Here, since there's 2 ones, parity is even, so there's no error. Now we just go from down to up. So we write it down as 0, 1, 1, 0, which is essentially just 5. So what this means is we have an issue at our 5th bit, right? So our issue is with our 5th bit. So that means sorry, this is 4 plus 2 is 6, my bad guys. This is 6th bit. So we have to, I believe the issue is 6 bit, so to change the value at 6 from 1 to 0. So our error corrected Hamming code will be 0, 0, 1, 0, 0, and this is a 6th bit. Instead of 1, it should stay as 0. 7 will stay as 0, 8 will stay as 1, 9 as 0, 10 as 0, 11 as 0. Yeah, so this will be a corrected parity bit. Right. I think that should be all right. Okay, so that is essentially Hamming code, and this is another very short question they'll ask. They'll also ask you guys to create Hamming code as well. I think it's in this paper. Yeah, so encode this into even parity and odd parity. So I'll just quickly do this as well. So the data bits which we have is 1, 0, 0, 1, 1, 0, 1, 0, 1, 1, 0. They want an even and parity bit. So first things first, let's see how many message bits we have. So that's 3 plus 6 plus 9 plus 2. So 11 message bits we have. So again, going back to the formula, which is 2 raised to p plus m plus 1. So if m is 1, so that'll be p plus 12, then equal to 2 raised to p. If we take p as 4, we'll get 16. So 16, so it matches, right? I guess. So it matches. So 16 is equal to 16. So we can take our parity as 4. So if you're trying to just draw this down, we will have our first bit as parity number 1, second as parity number 2. Then we put our message bits, and this will be 0, 1. No, my bad. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13. So we have parity at 1, we have parity at 2, we have a parity at 4, we have a parity at 8 as well. So we'll just fill in the message bits of the rest. So it's 1, 0, 0, 1, 1, 0, 1, 0, 1, and then we have 14 and 15 as well, which will be 1, 0. So starting off with parity number 1, we look at every odd number parity. So it'll be 1, 3, 5, 7, 9, 11, 13, 15. Right? So here we can see that if you're writing this down, it would be some P. There will be P1, 3 is 1, 5 is 0, 7 is 1, 9 is 1, 11 is 1, 13 is 1, and 15 is 0. So if you're doing even parity, we need even number of ones. So there's 2, 4, 5. So we need P1 to be 1, right, for even parity. So P1 is 1. I'll just write this up here. And we'll start for P2. So P2, the way I remember it is essentially taking every second number. So assume there's a 0 here. Assume there's a 0 here. So I take every second number. So we leave these two out. We take 2 and 3. We take 6 and 7. We leave 2. We take 10 and 11. We leave 2. We take 14, 15. Right? So we check. So P2, comma 1. Then we take 6 and 7. So it's comma 0, comma 1. Then we take 10 and 11. So it's 0, comma 1. And we take 40, 50, which is 1, comma 0. Now again, if you check how many ones are there are 4 ones. So our P2 should be 0 to satisfy even parity. Now we want P3. So the way I remember P3 is similar to P2, but here instead of taking every 2 terms, I take every 4 terms. So I leave the first 4, take the first 4, leave the next 4, take the next 4. So here it'll be P3. It'll be P3. And then from P3, we'll take 5, 6, and 7, which is 0, 0, 1. 8, 9, 10, 11 we leave. And we'll take 12, 13, 14, 15, which is 0, 1, 1, 0. Here we have three ones, so we need P3 to be 1 to satisfy even parity, right? So we can take P3 to be 1. And close this out. Now we'll go to the final, which is P4. So for P4, we take every 8 term. So we leave the first 8, we take the next 8, essentially, right? Or how much ever that is, till 8. So we take P4, we take 1, 0, 1, 0, 1, 1, 0. There are 4 ones here, so even our P4 is 0 to maintain even parity. So if I were to write our message code right now, it would be, I'll just add another 1, 0 here at the end. So here I would change our P1 to the P1 to 1. I would change our P2 to 0. Change our P3 to 1. And I would change our P4 to 0. So this is for even parity. For odd parity, all we have to do is just complement the parity bits. So for odd parity, what we can do instead is just make it 0, 1, 1, 0, 1. Oh, sorry. This will be 0, 0. This will be 1. We complement the zeros to be 1, 1, 0, 1, 0, 1, 1, 0. So all we do is we just complement the parity bits and keep the message bits the same. So this is for even, and this is for odd. Right. So that is your parity Hamming bits as well, which is also a very short question that they can ask. Well, let's just see the answer is correct. What's question number 4? 1, 0, 1, 1, 0, 0, 1, 0. Yeah, okay, cool. Okay, yeah. So these are your show questions they can ask. All the combinational circuit questions. So your half adders, full adders, your parallel adders, your half subtractors, your full subtractors. Learn how the outputs, the Boolean logic of the outputs, they will for sure ask you to use these half adders and your other combinational circuits to create some sort of Boolean expression. And it's just some way of manipulating your half adders to get the desired output. It just comes through practice. And learn your comparators. Again, learn how to handle multiple bit comparators. So 2, 3, 4, 5, 6, whatever. They can ask you any number of bits because it's very simple. It follows a pattern, which we've also discussed. And then after comparators, go through your decoders. Learn how to create larger decoders from your smaller decoders. Remember, use your smallest decoders as your enable activator. So you essentially have use your smallest decoders to control your enable pins for your larger encoders or decoders. And with that, you can build a massive decoder structure using smaller decoders. learn about encoders, learn about priority encoders, learn how we control the difference in priority, and how they can ask you to draw a truth table with different MSBs and different LSBs. They can ask you any sort of variation just to try to trick you, basically. And yeah, I think I think that's it. I think that's all. Yeah. So these are all the basic concepts that they will ask you, and yet be very sure in your K maps. I have gone through, I think, all the different ways that you can form groups with and without broadcast. And I think, yeah, that's all. That's the entire Midsem portion. So if anyone has any other doubts, you can feel free to ask me. We have half an hour left. Yeah, if anyone has any doubts. Hello.
Yes, we can hear you. Actually, I can say for myself, like I've only read the PPTs and done the theory. I've not solved questions as such, so I don't have doubts. And like today, like you solved the questions, I can understand, but I have to do it on my own, obviously.
Yeah, no, I'll share with you all these. Like, I have a Google Drive which my friend made. I'll
Yeah.
just share it with you, and yeah, I think it'll be great. It has all the solutions, so you can see if your answers are correct or not. And
Yes.
yeah,
And it's just that there's so much to learn in these topics. Like,
is this is there so much to learn?
yeah, all the topics that we just discussed today, there is so much to learn in all of these.
No, no. Actually, if you look at it, it's like all related. Yeah, basically everything you've learned until quiz was sort of a base. Like you're learning the ABCs of DD. Now you're applying them. So you're applying them to half adders, full adders, and everything. If you really think about it, if you're confused on how this comes about, just go back and think about the truth table, and from that you can have a Boolean expressions, and from that you can create a circuit designs. Everything can be what do you call traced back and downwards in DD. It's just that if you keep doing that, you'll end up spending a lot of time which you don't have during exams. Yeah, so that's why it's preferable you learn the circuits. I'm not saying mug up because it's kind of intuitive. Once you do it again and again, you'll sort of understand how these circuits come about. But yeah, it's if you trust me, good DD is not that difficult because it's especially midsem. Midsem, I think, is your best bet in getting pretty good marks because after this you start learning about latches, flip flops, memory. That's where it gets little more trickier. This is relatively, comparatively, a little more easier. So yeah, it's pretty chill. Yeah.
Yeah, I'll work on it. Actually, our quiz was like pretty easy and basic. Like we didn't even have K-maps in our quiz. The portion was still before K-maps. So
Yeah, exactly. So
yeah.
quiz, midsems, like it's pretty basic level. Even quiz two is also pretty basic. Even compre gets a little confusing because of all the memory and all the SR flip flops, but that's just through practice. But yeah,
Mm,
I'll share this drive link. There'll be an email sent from MTC, so that email will have this drive link with all the resources for you guys.
yeah, cool.
You guys have any doubts? Do you have any doubts besides numbers? Sorry, I didn't hear.
Not as such.
Okay. All right then. Fine then. I think we can end the session then. Thank you guys for coming.